Hello, everyone, and thank you for viewing this talk today. My name is Abhinav Malhotra, and I'm a postdoctoral researcher at University of Delaware. The title of this talk is Thermal Analysis of Structured Reactors for Microwave Reaction Engineering. If you look at a typical chemical process, we find that to drive the reactions, we have to reach a very high temperatures, and therefore we can term these processes as thermochemical, wherein a high temperature allows us to break down, for instance, an alkane to get an alkene, which can be used in downstream processes. However, with an eye on efficiency and emissions considerations that are fast becoming uh, relevant to our survival, we find that we have to transition to more process intensified technologies. And electrothermochemical conversion processes are one such area which can help us reduce our emissions. In this paradigm, the energy to drive the reactions is provided by electromagnetic energy in different forms. This comes with more advantages than emissions. For instance, it has been shown that by directly heating the reactor, we can reduce the temperature gradients that evolve in this system, which can lead to more intensified heating, allowing us to utilize the catalyst better and, of course, with more efficiency. So, with this motivation, today I'll be talking about using microwaves and how can we tailor their use in heating reaction domains. If you look at microwave heating, we find that since the ability to absorb microwaves is dependent on the material with which they interact, they can be used to obtain low gas temperatures and high solid temperatures. This allows us to do selective chemistries wherein the solid catalyst is directly heated, allowing us to increase the heterogeneous pathway while the homogeneous gas phase reactions can be suppressed. In the literature, this has been shown to increase the selectivity, in this case for isobutylene when converting from butane. And this has been achieved by the use of structured reactors or monoliths in which both the gas phase and the solid phase interact with each other. The gas phase being microwave transparent, that is, by not absorbing microwaves directly, the solid heats up to a higher temperature, leading to this hypothesis of selective heating. However, in the absence of direct measurement of gas phase temperature, this hypothesis cannot be proved conclusively. The direct measurement of gas phase temperatures inside channels in microwave heating is challenging because we can't use our traditional techniques, for instance, thermocouples, because they interact with the electromagnetic field of supply, thereby leading to erroneous measurements. And so this motivates our study, our computational study, where we want to use models to predict both the gas phase and the solid phase temperature. And even more, so we want to understand how can we engineer the solid fluid temperature gap. So armed with these motivations, we approach this problem where we have three distinct length scales to consider. We have the length scale of the microwave cavity in which the structured reactor is placed. The dimensions of the structured reactor are chosen so that the overlap between the electromagnetic field and the structured reactor is maximized. And within the structured reactor, we have these channels of a few millimeter diameter. To solve this problem computationally, we first need to solve the Maxwell's equations, which gives us the distribution of the electric field in the space. Using this electric field, we can figure out the heat generated in the structured reactors, and then coupling them with the heat transport equations, which is the Fourier's law and the convective equations, we can close this loop wherein the material properties that we use are influenced by the temperature predicted by the simulations, and we repeat this until convergence is achieved. In terms of experiments, we have a similar dimensions of the microwave cavity, which gets its power from a antenna, a coaxial antenna, and the structured reactor is placed inside a quartz tube. Quartz is microwave transparent, so it allows microwaves to go through it and interact with the structured reactor. The power deposited in this cavity is a function of the frequency at which these experiments are run. So to validate our computational model first, we consider a solid silicon carbide cylinder under no flow conditions. That is, there is no flow of gas in these experiments. The solid silicon carbide cylinder is modeled, and two predictions of the model for two different spectral emissivity values are shown here by these two lines. The black spheres tell us the experimentally reported value of power absorbed by this solid silicon carbide cylinder. We find that there is a degree of mismatch here. However, if we offset the experimental values by the empty tube offset, that is the loss value that is reported in the experiments when there is no sample loaded inside the quartz tube. These empty tube offset or these empty tube losses can occur because the microwave cavity is made of metals, and even though computationally we model them using an impedance boundary condition, in reality there is a dissipation that can happen in the metals as well. Furthermore, there are leaks that may exist in an experimental system. We find that the temperature maps predicted by the model as well as the experiments are in close agreement. We then apply the model to a silicon carbide monolith still under static conditions. This monolith has 21 square cross-section channels of 1.3 millimeter size. And we find that the temperature predicted by the simulations, the temperature spread as well as the average temperature is in good agreement with the experimentally measured values. One of the reasons why we prefer structured reactors over traditional configurations such as fixed beds is because we find that the structured reactors give us a very isothermal temperature regime without the formation of hotspots. So overall, we find that our model is in good agreement with experimentally measured temperatures of solid structures. Next, we want to apply our model to predicting temperatures under gas flow. And so here the gas flow is entering from the left and exiting from the right side. And I'm showing you a temperature map along this axial line shown here. So there are three significant things that I want to draw your attention towards. One is the finding of localized heating within the quartz tube. So downst upstream of the monolith as well as downstream from the monolith, we find that there is no direct heating, and gas phase temperatures rise up to meet the monolith wall temperature. This is because there is a selective heating of the structured bed itself or the monolith walls, and only these walls directly absorb microwave energy. We also note that within this monolith region, thermal transport is very important, as at this flow rate, which is 100 milliliters per minute, the two phases, that is the gas and the solid phase, almost equilibrate. We also validate these predictions with experimental tools that are available to us. So using an IR camera, we measure the temperature of the solid walls, and we find that it's in good agreement. Downstream of the monolith, we can use thermocouples as they no longer interact with the electromagnetic field, and we find that they also predict a rapidly reducing temperature profile. The importance of thermal transport can also be seen in the cross-section temperature map inside the monolith, where we find that the temperature gap between the walls and the fluid is suppressed. So overall, we find that under certain conditions, we don't see selective heating, while localized heating seems to be dominant. One question that we ask ourselves is how dependent is this selective heating on flow rates? So we conduct simulations for different flow rates, and we find that for very large flow rates, which is in the order of 5,000 milliliters per minute, the temperature gap can be sustained through the length of the monolith. Another important finding that we have is that with increasing flow rate, the average temperature of both the fluid, shown in blue, and of the solid wall, shown in red, goes down. And as mentioned earlier, the temperature gap, which is the difference between these two lines, begins to open up. So overall, we find that short residence times avoid thermal equilibrium and can be used to maintain the temperature gap. We're also interested in knowing what other properties can we control to control this temperature gap. But before going there, I want to talk about localized heating that we observe. So with our simulations, we find that for two different flow rates, if you're using microwaves for heating, the region upstream of the monolith is in blue, which shows that it's at low temperatures, while in a conventional heating furnace, where the whole of the quartz tube would reach a certain temperature, we find that this is not true. And on an average throughout the quartz tube, the temperature is higher when heated conventionally over when heated with microwaves. If you're interested in knowing the implications of this in reaction systems, my colleague Weiqi will be giving has a presentation in process intensification section, and he'll be there to address your questions on Friday from 8 to 9. So coming back to understanding the temperature gap, so we also conducted CFT simulations of a single microwave heated channel where the fluid enters from one end in a solid region of 1 millimeter thickness, which absorbs 2 watts of microwaves, and then it flows through the system. We consider two different fluids, air and toluene. With air, we find that for residence times in the order of zero point 0.1 seconds, the temperature gap is maintained. With toluene, however, this temperature gap can be maintained with, residence times in the orders of 5 seconds. So clearly, this tells us that with shorter residence times, we have a slower thermal equilibration. Also, for gases, they have low thermal inertia, and therefore they equilibrate faster uh, with the solid walls compared to liquid phase, for instance, toluene, and thereby they minimize temperature gradients. One significant finding that we have is that since we're using silicon carbide as our wall, we find that the wall temperatures are nearly isothermal. Uh, and that's because silicon carbide can rapidly dissipate heat throughout its own volume. To understand the evolution of temperature, we also construct a pseudo-homogeneous model assuming a constant wall temperature and a fluid inlet at T0, shown here by Ts and T0. The heat transfer between the walls and the fluid is lumped into the heat transfer coefficient H, which can be determined using the Nusselt numbers. And under these assumptions, we find a thermal equilibrium time constant given as R square by Nusselt times alpha, where alpha is the thermal diffusivity. We compare the pseudo-homogeneous model to the CFT model shown on the previous slide, and we find that both of them agree very well for a Nusselt number in the range of 3.66, which is what you would expect for a fully developed flow. Importantly, for air, we find that the thermal equilibrium time predicted by this expression is of the order of 25 milliseconds, while for toluene, it's of 2.5 seconds. However, at 100 milliliters per minute flow in the monolith, the residence time is in the order of zero point 0.5 seconds. And therefore, at these large residence times compared to the thermal time constant, the gas and the solid temperatures equilibrate with each other. This also tells us there's an opportunity to tune the equilibrium time constant using the channel size as it scales quadratically with the radius of the channels. So overall, we showed that the heat intensification in the small channels leads to minimal thermal gradients when the equilibrium thermal time constant and the residence time are of the same order of magnitude. And the localized heating is better suited to explain the increased selectivity that has been reported in literature in these cases. We also showed that there is opportunity to tailor the temperature gap using different fluids as well as the dimensions of the channel. So broadly speaking, we showed two things. One, that we can rationalize the mechanisms for improved selectivity, even when the flow rates are low, using the mechanism of localized heating that is provided only by microwave heating. And secondly, we also established that the predictive models created by accounting for all the relevant physical phenomena can be used as a method to probe both the solid phase and the gas phase temperature, especially under electromagnetic heating. With that, I would like to acknowledge the contributions of our collaborators at University of Valencia and University of Zaragoza, as well as the support from the Vlachos group. I would also like to acknowledge funding from RAPID. And if you have any questions pertaining to this talk or for any other collaborations, you can email me at this address. Thank you for your attention.